Okay. So now, when we studied Gaussian random vector, we talked about covariance, right? Or when we looked at x1 comma x2, we saw what is covariance. If you have a Gaussian process, what do you mean by covariance? So essentially, the way to do that is, you take two time instances, let's say t and tau. You have x of t and x of tau, two random variables, and I can see what is the covariance of that, right? So the covariance will depend on both t and tau. So it's called a covariance function. Okay, so the covariance function, I'll call this as kx of t comma tau, okay, of a stochastic process. Well, this is very general definition, but when you apply it to Gaussian, it makes things very simple. Okay, stochastic process. Let's say x of t belonging to t, right, is defined as. How do you define this? So, okay, let me write it here. So, k x of t comma tau is defined as you take expected value of x of t minus the mean of x of t. X of t is a random variable times x of tau minus the mean of x of tau. Right? So this is the covariance function. This is true for all t comma tau belonging to tau. Okay. Okay. Is that fine? Is that fine? Okay. Now, let's see what happens if this is Gaussian process. So
Hello, sir.
suppose, yes.
Sir, here when mean is 0, I mean e of xt and e of x tau is 0, then it will become autocorrelation, right?
No, right? Why do you say that it's the mean is 0, it will become autocorrelation? Autocorrelation is when you take t equal to tau.
T.
Sorry, yeah, it is this itself. In fact, this itself is an autocorrelation covariance function. Now, you are not taking two different stochastic processes and looking at the product expected value, right? You are taking the same stochastic process and looking at the covariance. So it's called the autocovariance function.
Yes.
Okay. So if you have two different, let's say x of t and y of t, and then you look at x of t minus expected of x of t into y of tau minus expected of y of tau, then we say that it's cross covariance. Okay. Yeah. So now, if you have, let's say, you take a Gaussian stochastic process, x of t1, x of t2, and so on, x of tk. That means you fix k, any k. K could be 100 billion or k could be 2, right? And the time instance t1, t2, etc., tk is arbitrary, any time instance, no matter what, right? So this is jointly Gaussian, right? It's jointly Gaussian. So what will be the mean? The mean vector will be easy, right? So it's expected value of x of t1 and so on, expected value of x of tk. Do you agree? Right? Do you agree?
Yes, sir.
What is the correlation covariance function? See, first one would be x of t1 times minus expected value of x of t1 times expected value of x of t1. So this is nothing but kx of t1 comma t1, right? All the diagonals will be like that, kx of tk comma tk, right? So what will be the ijth entry? Ijth entry would be kx ti comma tj. Do you agree? And so on. So what this implies? This implies that you need to know the mean function of the stochastic process and you need to know the covariance function of the stochastic process. If I know these two, that will describe the entire distribution, joint distribution of a Gaussian process. Okay. So essentially, I'll just refer, I won't write this. This is theorem 3.6.3 in the book. Okay. Essentially says that if you have a Gaussian process, the covariance function and the mean function for each time instance tau and t describes or specifies the joint distribution of this Gaussian joint probability density for all possible combinations of these random variables. Okay, is this understood? Fine. Yes or no? Hmm?
Yes, sir.
Hmm? Yes. Okay. Any questions? So this is important, okay? So you should understand what this is. So essentially, if I know the covariance function and if I know the mean function, I know the mean of all the means of any random vector, right? And I also know the covariance of that random vector. So means, covariance function and mean will specify the joint distribution. Is that okay?
Yes, sir.